Today we are going to continue working on our project Euler solutions. I believe last time we had solved project 11, solution 11. So this one, largest product on a grid, and we want to continue today. I think we did it. So yeah, we did solve this. So let's try to solve next problem. Highly divisible triangular number. So let's create a new Jupyter notebook in Python 3 and let's start. So what is this problem? We will call this problem 12. And let's copy the problem. Problem 12, it is something called a highly divisible triangular number. Okay, let's figure this out. The sequence of numbers, so let me put this in like that. Let me put this in like that, like that, and okay. So the sequence of a triangle number is generated by adding the natural numbers. So the seventh triangle number would be 1, 2, 3, 4, 5, 6, 7, and is equal to 28. The first term would be 1, 3, blah 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 blah. The first 10 terms would be something like that. Let's list the factors of the first 7 triangle numbers. So 1 is 1, 3, the factors are 1 and 3, 6, the factors are 1, 2, 3, 6, 10, the factors are 1, 2, 5, 7. We can see that 28 is the first triangle number, so 28, which corresponds to 7, is the first triangle number to have over 5 divisors. Okay, what's the value of the first triangle number to have over 500 divisors? Okay, okay, how do we solve this? So the triangular number looks like this. It is 1 plus 2 plus 3 plus 4. That would be the triangular number for 4. So that's that over there. So if you have a triangular number, let me see, is that what it is? Yeah. So let us say that you have a number n equals 4. Then what is sum of range that goes from 1 to n plus 1, and that's what it is. But there's a better way of calculating it, I think, and the way you calculate it is equal to n into n plus 1 by 2, and that is the sum of a series. So you add 7 to 1 and 6 to 2 and 5 to 3 and then sum it all up. So that's how you get that, and that you will get 2 of those things, so you divide by 2, so you get that. So that's one way of writing the same number. So the series solution of 1 to n is equal to that. So I think we should be able to use this formulation over here. So how do we find the factors of this? So we already know that the factors of the series from, let's say, 1 to 7, n equals, and if we put n equals 7, then we should get the number 28. And we want to find the factors of n and n plus 1 by 2. So we can find the factors of n, and we can find the factors of n plus 1, and n times n plus 1 will always be even, because either n or n plus 1 is going to be even, and as a result we divide that by 2. So that's okay. Let's write a function that finds the prime factors. So 5 divisors. Okay, so prime factors. Okay, so before we find the prime factors, we need a list of primes. Over 500 divisors. Okay, which basically means that if we have prime divisors, okay, if we can find the prime factors, then we can figure out the number of divisors based on the prime factors. So let's try to find the prime numbers. First 500 prime numbers. Okay, so primes equals 0, and I believe we have in problem 10, if I remember correctly, we calculated the primes all the way up to some ridiculously large number. So let's do that. So this is what we're going to do. Find the find a set of at least 500 primes. Okay, and let's copy paste that solution. Okay, so let's go 500,000, and what happened? We haven't loaded NumPy. Okay, so let's look at the primes. Oh, we haven't. Okay, primes. So length of primes. We have 4,000 primes, so we have more than enough primes. We don't need this anymore. Let us conserve some memory. Okay, so we have a list of primes. Let's call this the appendix. Okay, set of primes. Okay, the next thing we want to do is we want to find the prime factors of n. So given n, find prime factors of n. So let's see whether we can find the prime factors of n, and we will also provide the primes. Okay, for factors. Okay, so how do we do this? Let's say we have the for p in range for p in primes if p greater than n brick. Okay, and we create a set of factors. Started with the factor 1, because as you can tell, don't worry about it. We want the prime factors. Okay, now if p n percentage p is 0, then that's a factor. Factors append p. Okay, and return factors. So that should give us the prime factors. Okay, so now what we want to do is let's check. So let's say n is 7. Find prime factors of 28. So the triangular number of 7 is 28. We want to find the prime factors of 28. What happened? Okay, so we also want to provide primes. Okay, so the prime factors are 2 and 7 for 28. 2 and 7, and it also has prime factors of the other factors are 1, 2, 4, 7, 14, 28. If I remember correct, okay, and what? Okay, so what about the prime factors of 7 primes? Fine, we should probably call it prime factors. Not prime factors is just easier. Prime factors of 28 is that. Prime factors of 7 is just 7, and prime factors of 8 is 2. Okay, so the prime factors of 8 is 2. That's the prime factor of 8. Let us also find the number of times 2 goes with 8. So that's the exponent. So let me see. If we have 8 log 8 and 2, what does this mean? 8. Is that I want to see whether you can directly pass the base. The natural log of x, log 2, log 1p, math log. What is that? Okay, numpy log of n of any base. Let's see if we can. Math.log. Okay, let's say import math log 8 and 2. That should give me, yeah. And if you already know that 2 is a factor, then what we can do is take the int of that and we have this. Okay, and I don't think we need to find the integer of that. Okay, so the idea is this. We want to okay, and we want to find the prime factors, and we also want to find and exponents. Okay, so we have n and we have the primes, and we can just do all of that, just copy all of that, paste it. And how do we deal with this? We have factors, and we will make it a dictionary. Okay, and factors of prime p equals, that goes import numpy as np, import math. Okay, factors p equals math.log, and let's take a look at 8 and 2. 8, we want prime factors and exponents, so now we should get a dictionary, and we see that for 2 there are these many exponents. Okay, what about 28? 28, okay, so I can't do this. I cannot use log. Okay, I'll have to do it the hard way. N factors equals 0, and we'll call this n factors, and while Ah, so I can just put while this over here, we can put n factors over here. N factors is 0. And while this is that, and n factors plus 1, and we divide n by equals p. So that should be okay. 2 and 3. Okay. So 2 is that, 3 is 0, 5 is 0, and 7. If n factors is greater than 0, we only care about, okay, so now we have this. 2 has an exponent of 2 and 7 has an exponent of 1. That's for 28. Okay, so now we have to figure out how do we get the number of factors. So it's 1, 2, 4, 7, 14, 28. If we have 28, so that's 1, 2, 3, 4, 5, 6 factors. You should be able to set this up if you have any combination of the prime factors, except that if a prime factor has an exponent, you should be able to skip that. Let me try something real quick. So this has 2, plus 1 is 3. 1, 2, 3, 4, 5, 6. 3 into 1 plus 1. 1 plus 1. Oh, down. Into 6. I think that equals the number of factors. I think this should equal the number of factors. I think so. Let's look at 21. So if I take this and this, yeah, I think that would be it. Okay, let's try a few. Okay, I'll just call this F. For F in F dot values, okay. I will say like that, and np dot product like that. Built-in method object is not okay. Values 6. I think that is the number of factors. I think it is a number of factors. Okay, how about 21? Or number of divisors. Okay. So, n equals like that. Okay. Def and divisors, and we take a number n and the primes, and we are going to get the factors, the prime factors, like that, and there's going to be n, and return n divisors. Okay, let's see if this works for 28. For, let me see, n in 1, about 1, 3, 6, 10, 15, 21, and 28. Print and divisors n and primes. 2, that's 2, that's 4, 4, 4, 4, and 6. Yep. All right. Now we have to convert n for, okay, range 100, 1, 2, and 100. List. Okay. 2, 3, 4, blah blah blah. Let's go to 100. And n equals int of m into m plus 1, like that, by 2. Blah blah blah. So if you go only up to 100, you will get, go up to 100. 100 has 54 divisors. We need many more than that. Something like that. Okay. Number of divisors, we will call it d, and if d is greater than over 500, then we will print d. We have to print value of the triangular number. What is the triangular number? Give me a second. 28 is the first triangular number, so this is the n is the triangular number. N. Okay, so let's start with 5. Why are we printing stuff? Wait. So 12 has 6 divisors. Wait, is that right? Where is it getting 12? Like I need to divide by 2. 28 has 6 divisors. 28 is the first triangular number that has over 5 divisors. And now we need to go to over 500 divisors. So it doesn't have 500 divisors. What do you know? And we have gone all the way up to 100,000. Let's print n and d. 240. Wow. Okay. This is getting ridiculously large. I think we don't have to. There should be a better way, because there is m and m plus 1 for m, and when m increases by 1, we should be able to find the prime factors of each of these things individually. Okay. And get the same numbers. Okay. Let's make sure we can do that. Okay. Let's print n and d. That's method 1. Print. Okay. But what we want to do is we want to memorize this so that it doesn't have to calculate something all the time, and we can also do the prime factors. Instead of calculating the prime factors of this, we can calculate the prime factor of this and this individually. Okay, so let's do that. N divisors n divisors of, so we'll call that d1, of m and n divisors of m plus 1 like that. And we should be able to, and this should be a much faster thing to do. Okay, so and then we will update d1 for let's create d3 equals this, d3 equals d3 dot update. So we'll copy everything in, or copy all of d1 into d3. We will, for v in d2 like that, d2 dot items if something in d3, k in d3, okay, then d3 k plus equals v, else d3 k equals v. And so d3 should be exactly the same as that. Find number of divisors, which is already the product. I don't want the number of divisors, I want prime factors and exponents like that. I want the prime factors and exponents, and then once I have the factors and exponents, I should be able to find, okay, I want the prime factors and exponents of this, and I want to make sure that this f, and let's call these prime factors and exponents, are the same. This should be faster, even though it does many more things, and I'll try and explain why. Okay, d1 is not present, this should be f1. None type is not iterable. Okay, if k in f3, oh, f3 dot update, I don't need to do this. Okay, I also want to print f over here, and n, I want to print f, and I want to print f. Okay, okay, so this has 3 For 3 it is 3 1. For this it is 2 1 and 3 1. Okay. This has 3 1 and has an extra 2 2. Okay. This has 2 1 5 1. This has an extra 2 1. Okay, so and this is because we are not dividing by 2 over here. So yeah, so we have an extra 2 which we need to reduce. Okay. Okay. The other thing that we can do is, if something is already available, I don't want to look it up, right? So that's I need to calculate m plus 1, but m should already be there from the previous step. Okay. So I will just calculate f1, so I don't actually need to calculate f1 from I don't need to calculate f1 all the time, because f1 should be there in the previous step. Okay, so prime factors like that, f1 like that, 2. So the first one is that, and we do all of this and we say f1 equals f2. This should be exactly the same thing. Okay, it is exactly the same thing. 2 to 10. All right. Okay, and then we need to reduce f3. Okay, f3 if f3 2 is 1, then delete f3 2. I think else f3 2. There you go, this is what we want. Okay, so now that we have this, the result of this, so this should be much faster. We don't need this. We don't need this stuff. N is ridiculously large. Okay. So we have that, and then the divisors we can calculate with through F3. Divisors is just this product, and it should be the product F of F3 dot values, and we can provide M and F3 and the divisors D. Okay, so we have for 2 the triangular number we don't want to calculate because it's very large. It can become very large. It's 2 4 4 4 4 4 4 4 4, and then we'll have 6, and it will continue. Okay, 6 9 6 and so on. Okay, so we have a method. We don't need to print this. Okay, we can go all the way to, let's say, something like that. And if D is greater than right now 6, okay, print D, but we also want to print M, and we also want to print M into M plus 1 by 2 by 2. Oh, let's stop this. Break. This should be an integer. Let's do integer division. Okay. Greater than 5. If we do 5, it's 7. The triangular number is 28. Okay, and it has six divisors, which is over 5. So we need over 500, and let's see where we are. Okay. Okay, so once we went to 1 2 3 7 5, we have this number for which the number of divisors is 576. Let's see whether this is correct. All right, okay, so we will call it a day for this video. Okay, we'll see you in the next video.